Welcome back to topic 6, an introduction to neural networks and deep learning. So in this series of slides, we'll be talking about how we actually train a neural network. That is, how do we actually update the weights of the connection between the neurons so that we actually learn a new function from the data. So the neural network learns through this key feature, right? The key feature is the iterative learning process where the data is actually being presented to the network one row at a time, and the weights are adjusted with the input values each time. After all the examples or all the rows have been presented, we start this process over again. So it's a very iterative process. And during this learning phase, the network learns by adjusting the way so that they are better able to predict the correct output for a given input sample. So imagine we have actually a function JW where JW represents the error in the weights and W is the possible configurations of weights. The initial configuration of the weights is represented by the dot, the black dot here. So that's actually the initial configuration of weights. And the basic idea here is to adjust the weights, move the configuration of weights such that the total error as represented by JW will be at a minimum. So we want to move from the initial point towards the low error or the minimum error point. Okay, and the way that we actually am able to do this is basically to move the configuration of weights in the direction that of the gradient, right? In the negative direction of the gradient. So depending on the gradient of the current configuration of weights, we want to move the black dot here away from the higher errors and closer to the lower errors. So we will look at the gradient and try to adjust it to a lower and lower value. And now this is actually the basic idea for the training of the neural network, and we will be looking at the algorithm that's been invented for some time now called the back propagation algorithm, which basically tries to adjust the weights in a manner that moves the weight configuration down towards the negative of the gradient or slope of the current function. Now, there are a few side effects that you should be aware of. First of all, sometimes there's not only one gradient, but there may be several different local minima. So there's one overall minimum, but there may be humps along the way, and so there are some local minima. So we need to be able to move the weight such that we will have some sort of momentum or velocity, so we can actually roll past the local minima and drop to the next, and ultimately be able to find the global minimum. So we don't want it to get trapped in a local minima. Secondly, the speed of convergence depends on something called the learning rate. So if we increase the learning rate, the ball or the black dot here will actually roll down the error slope faster. However, if the learning rate is, it will actually be faster if we increase the learning rate. However, it will overshoot the minimum and have this oscillating effect where it will bounce around the minimum for a long time if your learning rate is too large. So it's the Goldilocks problem again, right? If you keep it if you make too small, each iteration will be adjusted very slowly. So the ball will actually move very slowly to the minimum, but you'll be moving it smoothly. However, if you're not so patient and you want to be faster, you make the learning rate high. It will move fast, but it will overshoot and it will be oscillating around for a long time. So there is a value which is so-called optimal, where it will actually not be too fast, but you will actually also not too slow, so you will approach the minimum point in the most optimal manner. So the back propagation algorithm consists of two passes. The forward pass is just a signal propagation pass. So we will just be computing the weighted sum, pass it through the activation function, and send the output to the next few neurons. So we will just do it for every single neuron. So for this configuration here, this neuron, you have two inputs into it. You calculate the sum of these two and calculate what's the output value. Then you move on to the next neuron and get the two input values and multiplied by x1 and x2 and get this value. And then you move on to the last one and then you calculate the weighted sum of these two values. Then you move to the next layer where this output is basically the sum of all these values coming to it, and this one is actually the sum of all these three neurons coming to it. And finally, the output layer where it is basically the weighted sum of this neuron plus the weighted sum of the other neuron, and then you get a certain output function. So the forward pass doesn't learn anything because we don't actually adjust the weights. We just pass the signal in the forward direction. So the learning actually occurs during the back propagation, the backward pass of the back propagation algorithm. So in this part here, for the final output neuron, we actually calculate what's the error. Okay, so the actual value that is being predicted right now is y, but the target value is actually z. So there's an error of z minus y, which is the difference between those two values. So ideally, you want the error to be 0, but there's some sort of error delta now. And for the backward pass, the first part of it is basically to pass that error value backwards. That's why it's called a backward pass to the other inner neuron. So the way that it's actually being passed back is actually to calculate it based on the weights coming into that final output neuron. So as you can see here, this weight from this neuron to this neuron is actually W46. So the percentage of error that's actually passed back is actually W46 multiplied by delta. Similarly, for this one, is actually W56 multiplied by delta. So if the idea here is that if there is any error that's actually occurring at the last neuron, it's actually a fraction that's dependent upon the weight. Since the signals come from the two input neurons is affected by the weight from neuron. So if the weight is 0, it means that this particular neuron has no contribution to the error. So we won't actually pass any error to it. So that's the reason for multiplying. So we after getting it for this hidden layer, we will then need to pass it back to the first, it will pass it back further to the next first hidden layer. And just as before, the amount of error that's passed back is actually a weighted sum. So we will use W14 multiplied by this error here and W16 multiplied by that error there. And the total error that's back propagated to this particular neuron is actually the sum of the two. The weighted sum of the two errors multiplied by the weight coming into that particular neuron. So the weight coefficient is actually used to propagate the amount of error that it goes back into the inner layer neurons for the previous layer. Similarly, for this neuron, we get it from these two neurons, again the error, and then we propagate it according to the proportion that's determined by the weights from this neuron to that next neuron. And finally, for this neuron, again, is the weighted sum of the error in the other next layer's neurons, back propagated with the proportion determined by the weight of the connection between this neuron and the next layer. So after propagating the errors backwards, we will need to basically adjust the weights in each of these connections so that we will actually learn the function. Now, the way that we update the weights is actually the new weight is the old weight plus a learning rate for this particular neuron. So this connection here will have a new weight, W46 prime, which is the original W46 plus the learning rate meter plus the error in that node plus the slope that's associated with the output here multiplied by the output from the previous neuron itself. So the previous neuron multiplied by the slope, multiplied by the error, multiplied by the learning rate, plus the original value of the added to the original value of the weight will actually update the weight. So because we are going to be using the error which is negative, we actually basically going down the opposite direction of slope, right? So we know that from the earlier diagram that we want to move down the slope towards the minimum point. So for the other neuron here, this neuron is the same formula, is 5,6 plus the learning rate multiplied by the error multiplied by the slope at this output function and multiplied by the output from this previous neuron itself. After handling the weights that's attached to the output neuron, we then go to the next layer. So the errors here again have already been backward propagated. So to adjust the weights that were attached to the second hidden layer, all these weights here, we will apply the same formula again to each of this. And once it's done with this second hidden layer, we will move on to the first hidden layer. So this is actually for the second for this neuron, you update all those weights that are coming into it. For the second neuron, you update all those weights that are coming into it. with this set of formulas. Then we come to the first hidden layer, and then we'll update all the weights that are actually attached to the neurons in the first hidden layer, like this ones here. Again, using the same formula, is this weight is the previous weight plus the neta, the learning rate, multiplied by the error that's back propagated to this neuron, and also the slope at this neuron multiplied by the input value itself. Then we'll move on to the next neuron and also do the corresponding updates. So for this next neuron in the first hidden layer, we'll update those two weights that are coming into it. So finally, we will actually update the last neuron here that's in the first hidden layer and update the weights that are coming into it using the same formula again. So once this is done, we have actually updated all the weights in each of these connections in the simple neural network, and we will actually go through the forward pass again with the next set of data, and we will keep repeating this until all these weights actually eventually converge to a configuration that gives you the minimum error for the entire configuration for a given set of outputs. So you will have learned the mapping function that maps the set of inputs into a given set of outputs by updating all these weights. So all these weights, they actually take into account all the possible combinations of the input and output. So there are only two inputs here and one single output. So the total number of combinations is not very large between these values. So these weights that are already in these 6 neurons, right? They are more than enough to be able to learn all the possible combinations no matter how complicated the function is between x1, x2, and y.